All right, well at this point I'd like to go ahead and demonstrate a little debugging. We're going to look at a stop 80, which is a NMI hardware failure. Actually, we're going to look at a couple stop 80 bug checks. They're both the same stop code, but the outcomes of these crashes are completely different. So let's go ahead and take a look at the first one. All right, then we'll just fire up the debugger and go ahead and run it in administrative mode and proceed to open up our crash dump. Here we have a memory dump, and we'll get right on into the debugger, and we'll want to scroll back up just a little bit to read some of the information. So first thing worth pointing out that this is a Windows 10 kernel. It's actually build version number 14393, which is Windows Server 2016. Here we have 12 processors on the system, and it's of course x64 type architecture. As we scroll through the output, we can see that yes indeed it was a stop 80 or an NMI type crash. Someone forced this crash because the system locked up. Now you can see here that the debugger, before we've even typed our first command, believes it was caused by the refs.sys driver. That is the resilient file system driver. The debugger thinks that ref.sys crashed it, and many times the debugger is actually correct. Now, I wanted to preface this crash analysis because as Microsoft introduces new versions of Windows, you typically have a problem driver or a buggy driver. For example, when Windows 2003 first came out, Microsoft had just introduced the StorePort driver. This was replacing the old SCSI port mechanism. So when StorePort first came out, well, it had some growing pains, and you literally saw a lot of crashes going on. In fact, Microsoft literally had the hot fix of the month club for poor StorePort. We got so many new hot fixes, it was incredible. Same thing can be seen in like Windows 2008. At that point in time, Microsoft decided to do all the MPIO, the multi-path I/O system, by themselves instead of letting third-party vendors provide that functionality with things like PowerPath and SecurePath. So for quite a while in 2008, MPIO.sys was a big crasher, and we saw lots of hot fixes. The same thing happened in Windows 2012. That's when, as you know, Hyper-V really took off, and there was a driver called VMSwitch.sys, which was very much involved with the networking of virtual machines, and we saw a lot of crashes and a lot of hot fixes for VMSwitch.sys. Well, to make a long story short, now in Windows Server 2016, we are seeing a lot of crashes with the refs.sys driver. And that is because Microsoft is now really pushing refs instead of NTFS, the older file system. So as more and more customers start utilizing it, we're seeing a lot more crashes. So keep that in mind as we start out. Well, go ahead and issue a command to get us rolling, like bang analyze -v and -hang, because this was in fact a forced crash because the server hung. So we'll go ahead and let that run. And well, you can see here that it's scanning for threads. We'll go back and take a look at that. Just scrolling back up here. Here's where we issued the command. And you can see that it's scanning for threads blocked on locks, and it wasn't able to get the e-resource type, so we didn't get too much information there. But then it goes on and gives us lots of good information, such as the stack pattern, which we'll take a look at in just a moment. You can see the stack here to the far right. One of the commands we'll want to start out with is looking at the thread that was executing at the time of the crash. So let's scroll back up here. Here's the command bang thread that I issued, and we can see that there was some sort of Veeam deployment service running at the time. And the thing that we're interested in is the stack over to the far right. What was this thread doing at the time when we forced the crash? So let's go ahead and read the stack from the bottom up. You can see it was doing a system service, trying to look up an object, and then the filter manager driver got involved and ultimately handed it off to the refs.sys driver. And it's trying to do various things like network open create. It's enumerating a directory. It goes up here and it actually tries to lock pages in memory. At that point, it hands off control to the NT kernel, where the NT kernel is trying to wait for a spin lock exclusive and acquire. So on behalf of the refs.sys driver, we see the kernel now trying to wait for a spin lock for whatever reason, and then we got interrupted, and yes, the system was bug checked. So question is, why were we waiting for a spin lock? Well, we can explore a little more with the bang running-it command. So this, as you know, will show me what is running on each of the different CPUs. So let's go ahead and back up here to where the command started. Here we go. So I issued the bang running-it command, and we can see on CPU 0 what was executing. It appears to be something dealing with NTFS. We started here with a system service, once again handed off to the filter manager, which handed it off to the NTFS driver, doing some sort of directory control. It's actually trying to read an index buffer when it incurs a page fault. And to try and handle the page fault, you can see the NT kernel is doing some sort of resolving of the PTE, that's the page table entry, and it's trying to allocate a working set list entry, and then it's doing more work on the actual working set by rotating the head of the list and so forth. So it is doing real work right here on CPU 0. Things are moving along and it's adjusting the working set for whatever reason to handle the page fault that it incurred. So that's what's going on CPU 0. Let's go ahead and take a look at what's going on the other CPUs. Here we have CPU 1. Well, let's see what it was doing at the time. It was doing a system service, going through the filter manager to get to the refs driver. And once again, it was doing some sort of network create, trying to enumerate a directory. And then it tries once again to lock pages in memory. And the NT kernel says, sure, I'll go ahead and do that for you, but to do so, I need to acquire a spin lock, and there it sits, waiting to acquire this spin lock. So we now know what CPU 0 and CPU 1 were doing. Let's go ahead and see what CPU 2 was doing. Lo and behold, you'll see that it is doing the exact same thing. It is waiting for a spin lock. It was trying to lock pages in memory. So we've got some sort of scenario building here. CPU 3, what was it doing? Look at that. It's waiting for a spin lock once again. And if we keep on going through all this, we'll see that CPU 4 was indeed waiting for a spin lock. CPU 5 was waiting for a spin lock. CPU 6, CPU 7, all of the CPUs are indeed waiting for a spin lock, except that very first CPU 0 that we looked at. And you saw that it was doing actual work with the working set at the time. Here we are, CPU 10, CPU 11, that's the one that actually bug checked, and we know that it was waiting for a spin lock before we actually bug checked. So all 12 CPUs in this system are doing work. 11 of them are waiting for a spin lock, and the CPU 0 is actually doing some working set adjustments. So there's several things that we can look at. We can see if there was some sort of memory issue, since they all seem to be locking pages in memory and adjusting working sets. So if we do a bang VM command, and we can actually put the flag 1, which will show you just the system type information for the virtual memory. I scroll back up here to where this started. Here we go. There's my bang VM command, and it tells me things like the page file. How much space is free in the page file? Well, you could see based on its maximum potential size, most of the page file is free. So the system did not hang because the page file was full, which it can be a common reason. Now, how much available pages of physical memory are there? Well, there's quite a few pages, like 53 gig, so we didn't run out of physical memory either. We really don't have a memory problem per se, but that REFS driver was trying to lock pages, and the NTFS driver was trying to adjust a working set, and it seems that we have some sort of synchronization issue. So at this point, we've pretty much got it narrowed down to the REFS driver, so I'm going to take a look at that with the bang LMI command. It gives you some good information, but you'll find that the LMVM command with the REFS driver will give you even more good information, such as the product version number. So there it is, 10.0.14393. That's the build number we noted earlier. And this particular version of the driver is 1198. Same thing can be seen with the NTFS. LMVM of the NTFS module will show us the exact same version for that driver too. In summary, this is a spin lock hang. All the CPUs were busy trying to acquire a spin lock on behalf of REFS, and the owner of the spin lock is NTFS trying to adjust a working set. So this is a synchronization issue between REFS and NTFS. There's, as I mentioned, been numerous hot fixes for REFS in Windows 2016, so you want to find the most recent one that will fix your issue. So hopefully this gives you a good idea of how to go about troubleshooting a spin lock hang.